Okay, so in the last slide, we just ended taking a look at the formula. So I just wanted to explain this formula again for the geometric distribution. The probability that y is equal to k is the probability that y is equal to the first success on this given trial. So if it says probability y is equal to 3, that means the first success is on the third trial. So if it says y equals 10, the first success is on the 10th trial. This 1 minus p k to the minus 1, that's basically like saying 1 minus p is your failures, k minus 1. If k is 10 and I want the first success to be on the 10th trial, that means 10 minus 1 is 9. That means I'm going to have 9 failures before I get my first success. So just think of this as failures times successes. So this is the number, your probability of failure times how many failures you want times your probability of success. And notice you only have, you're only getting a success one time because you're getting one success on the 10th trial, so on and so forth. So if you want probability that y is equal to 10, that would be your probability of your failures to the 9th, because I want 9 failures, times your probability of success, which is on your 10th trial. Okay, so let's just take a look at the geometric random variable and what it looks like whenever we graph it. So this table right here shows the probability distribution of y. We can't show the entire distribution because the number of trials it takes to get the first success could keep getting larger and larger and larger. So when this says y I equals 1, that means the probability of success on the first trial is this. Probability of your first success on the second trial, so that would mean 1 success, 1 failure. Y equals 5. That would mean that you have 4 failures and 1 success on the 5th trial. Probability that y is equal to 6. Okay, so that means I have 5 failures and 1 success on the 6th trial. Now notice how the probabilities are decreasing as the number of trials gets larger, because that means you're taking more and more, you're multiplying more probabilities together, multiplying more failures and only 1 success on the last one to get this decimal. So notice how the decimal is getting smaller and smaller and smaller. So when we take a look at our distribution of a binomial random variable, it's always going to be skewed to the right. And the reason it's skewed to the right is because your probability of success on the first, second, third trial is going to be higher than your probability of success on the 50th trial. And if you think about that, because on the 50th trial, that's saying you have 49 failures and 1 success on the 50th, and that's a lot of decimals multiplied together, which makes your decimal smaller and smaller. So our successes on the first trials are going to be larger, and then as we increase the number of trials, the probability of getting the first success way down the line is going to get smaller and smaller and smaller, which means this distribution, no matter what we do, is always going to remain right skewed. Okay, so it's heavily right skewed. All geometric distributions are going to be right skewed, and the most likely value is 1. So that means the probability of getting your success on the first trial, that's going to be the highest probability because you're not multiplying any other decimals before that 1. The center of y is equal to 7. So in this case, we'd expect it to take 7 guesses to get our first success. And we'll go over how we get that number in a minute. So in this case, the standard deviation is 6.48. If the class played the lucky game many times, the number of homework problems they would receive would differ from the mean from 7 by an average of 6.48. Okay, so basically this is from our lucky guesses question. So this is saying it's going to take 7 guesses to get the first one correct. Okay, so the only thing that we really care about with a geometric random variable, we don't usually use the standard deviation, and that's because it's right skewed. So remember, when it's right skewed, we don't necessarily use the standard deviation, and we're not going to get into the interquartile range or anything with geometric distributions. So if y is a geometric random variable with a probability of success, then the mean, or the expected value, so we're going to use both terms in this, mean and expected value, is 1 over p. So the mean of any geometric random variable is 1 over the probability of success. So when we had 1/7 was our probability of success for our lucky day game, 1 over 1/7 just give us 7 guesses to get our first success. So on average, it would take us 7 guesses to get our first success. Okay, all right, so what's on the AP exam formula sheet? This is on your AP exam formula sheet under geometric probabilities. Notice it's the exact same thing as a binomial, but with no binomial coefficient. Just understand when this says x is equal to n, this is saying x is equal to the first success on the 5th trial, so on and so forth. You have 4 failures raised to the 4th times 1 success on the 5th trial. Now, this one right here is a little bit different. So this probability that x is greater than n. So that's like asking the question, what's the probability that it takes more than 5 trials to get your first success? Okay, so what's the probability it takes more than 5 trials to get your first success? So this is 1 minus p to the n. All this means is what's the probability that it takes more than 5 trials to get my first success? This is saying I have at least 5 failures. So this is the probability of your failures raised to how many failures you're going to have before your first success. So all you have to do is say greater than 5. Okay, so that means I have at least 5 failures. So probability of failure raised to the 5th. And then your expected value or your mean, that is on your formula sheet, they mean the exact same thing. So it's 1 over p. So how many trials do you expect to get? How many trials do you have to do before you expect to get your first success? Now just remember, don't ever round this one, even if it comes out to a not pretty number. Now, there are Okay, so I apologize. These formulas are not on the AP exam formula sheet, but just remember that geometric settings are independent, and you don't even have to necessarily use the geometric rules in order to do these questions, because they're basically the same type of questions that you did on whenever you just did your probability unit. Okay, so just keep that in mind. Okay, so let's do a couple examples. So in the board game Monopoly, one way to get out of jail is to roll doubles. Suppose that a player has to stay in jail until he or she rolls doubles. The probability of rolling doubles is 1 out of 6. So I want you to explain why this is a geometric setting, define the geometric random variable, and state its distribution. So remember, that's approximately normal, approximately binomial. In this case, it's going to be approximately geometric. Find the probability that it takes exactly 3 rolls to get out of jail. So go ahead and try this and see if you can do it based on what we just did. And then finally, find the probability it takes more than 3 rolls to get out of jail. On average, how many rolls should it take to escape jail in Monopoly? And recognize that letter E is when it says on average, how many rolls should it take to escape jail? That's basically like saying on average, how long is it going to take to get your first success? Okay, and then the last question is, what's the probability that it takes longer than average to escape jail? What does this probability tell you about the shape of the distribution? So this letter F is still the probability that something is greater than something else. Okay, so let's just go through this one. Why is this geometric? It's binomial. There's 2 possible outcomes, doubles or no doubles. It's independent. Each time you roll a dice doesn't affect the other dice. The number of trials is not fixed because we're basically counting the number of rolls until we get our first success or our first doubles. And then the probability is the same for each roll. So the probability of rolling doubles is 1/6 each time. That's not changing. All right, so we're defining the random variable. That's like saying y equals blank and then stating its distribution. Okay, in this case, you can define it x, y, whatever. Sometimes it's nice to use y just to show that it's different from the binomial distribution. Okay, but notice here we said x is the number of trials until the doubles are rolled. So we're saying we are doing this until we get our first success. Okay, all right, so here is the probability distribution. Now notice when it says state its distribution, that's a distribution table. That was tricky there. We haven't done this in a while, where we have x, okay, so how many trials until doubles are rolled, and then the probability of that occurring. So 1, remember that this is the probability of success on the first trial. 2, probability that I got a success on the second trial. 3, probability that I got a success on the third trial. And then we're going all the way up to n because we can't state this is the number of trials until the doubles are rolled. It could take n number of trials. So n just means like, well, how many trials is it going to take us? So that says, now notice this 1 minus p is saying how many failures, n minus 1. Okay, so that was the number of trials minus 1 because I have 1 less trial of failure. So here's my failures times 1 probability of success. Okay, that one was a little bit tricky. So what's the probability that it takes exactly 3 rolls to get out of jail? You don't necessarily have to have this table to answer that question, but x is equal to 3, so that's telling us on the first and second roll I have a failure, and on the third one I have a success. So probability of failure 5, 6, 5, 6. 1, 6 is my probability of success. Okay, all right, letter D says find the probability that it takes more than 3 rolls to get out of jail. So that's the probability that x is greater than 3. So that basically means I'm going to have at least 3 failures. I could have more than that, but I have at least 3 failures. So 5, 6 is the probability of failure raised to the third because 3 failures equals 0.5787. Okay, now when I say the probability takes more than 3 rolls to get out of jail, the first 3 have to fail. Basically, that's saying then after that, we're going to have all successes. We're just going to keep on rolling successes. On average, how many rolls should it take you to escape jail? You should hopefully recognize that that is your expected value question. So our expected value, show your work for that, is 1 over the probability of success, which in this case is 1/6. So 1 over 1/6 equals 6. And you can use your calculator to answer that question, no problem. Just make sure you show your plugins. All right, so what's the probability that it takes longer than average to escape jail? So you would have to be able to answer question E first. Okay, so it's going to say the probability that x is greater than 6 because it takes on average 6 trials to escape jail. We want the probability that it's longer than average. So this is saying that I have at least 6 failures. Okay, so probability that x is greater than 6, so 5 out of 6 is my probability of failure. I want to fail at least 6 times. Okay, so it's only a 33% chance that it takes longer than average to escape jail. So what does this tell us? It tells us that the graph is skewed to the right. Why? Why does it tell us that the graph is skewed to the right? Because as I increase the number of failures before my first success, the probability is getting smaller and smaller and smaller, which means that tail is getting longer and longer and longer. Okay, so go ahead and try this one on your own. I'll go over the answer on the next few slides to see how you did. Okay, so what's the probability of drawing the first red marble on the second draw? Okay, so red, we know that the probability of red is 20 out of 35, so x equals 2. So this is like saying the first one is a failure, 15 out of 35, and then the second one is a success. Okay, probability of drawing the first red marble by the second draw. Okay, so this one, look at the wording to this. This is a little bit tricky. By the second draw. So by the second draw means that I could get the first red marble on the first draw or the second draw. And remember with the word or, you're always adding. So what is the probability that x is less than or equal to 2? Now there's 2 ways to do this. You could add up the probability of on the first draw plus the probability on the second draw, okay? Or you could take a look at the complement. The complement here, remember 100% of them, okay, is every single possibility that I could have up to 35, because there's only 35 marbles, but 1 minus the probability that x is greater than 2. So x is less than or equal to 2. If I take the whole thing minus greater than or equal to 2 is going to give me my probability of sort of what's left over. What's left over is less than or equal to 2. So remember we said here probability that x is greater than 2 means I'm going to have 2 failures, okay, and then I end up getting my first successes. So 1 minus the probability basically of 2 failures here. Okay, which gives you 0.863. Okay, so what's the probability that it would take more than 2 draws to get a red marble, which is what we kind of answered on the last page. Probability that x is greater than 2. That means I'm going to have 2 failures and the rest of them are going to be successes. So 2 failures, 15 out of 35 squared, because there's 15 that are not red, and that gives me 0.1837. What's the average number of marbles you'd have to draw to get a red marble? You have to understand that that's the expected value. So we know it's 1 over the probability of success. The probability probability of success in this case is 20 out of 35 because 20 out of the 35 marbles. And you can do that on your graphing calculator is 1.75 marbles. Just understand that please do not round this. I understand that you can't draw 1.75 marbles, but please, please, please do not round that. And the only thing else that I would have to say is please make sure that you go to the graphing calculator section and take a look at how to do a lot of these questions on the graphing calculator. That'll show you how to do the geometric PDF and CDF also.